I want to talk a little bit today about how to combine multiple forces into one, what we call resultant force. And then I want to talk a little bit about how that might affect an object and how that might produce, for example, an acceleration or any other effect on this object. I then want to go into an idea of something called equilibrium, which is sort of a counterbalance to the forces acting on this object. So I've set up a sample problem here, and I'm going to have a 10 kilogram object. It's acted on by 3 concurrent forces: a 30 Newton force to the north, a 50 Newton force to the west, and a 10 Newton force to the east. I want to know what the resultant force is on this object, and I also want to know the acceleration this object will experience. That's kind of the first part of this. So let's explore this idea together. First, let's draw a little force diagram. Let's build our object here, and I'm going to put it actually a little bit more to the side here to give myself some room, but we'll say there's a 10 kilogram object. We'll say there are only 3 forces acting on this object. So let's analyze the 3 forces acting on this object. Well, I have a 30 Newton force to the north, so we draw that, 30 Newtons. We have a 50 Newton force to the west, okay, and we have a 10 Newton force to the east. And I'm going to put this as a negative 10. And the reason I'm putting that as a negative 10 is because it's in the opposite direction of that positive 50. If there was a downwards force here, I would also have to define that as negative, because direction matters, because force is what type of measurement? Force is a vector. So you want to remember, force is a vector, so direction matters. Force is a vector, so direction matters, meaning signs matter. You want to use positive and negative signs for opposite directions. You want to remember that that is the case. So let's break down this force diagram together, and there are a couple of ways to do it. One way is to draw these in a method we call tail to tip. And if we draw these tail to tip, we're going to say, okay, well, I can do these in any order. Let's say if I do I'll do the 50 Newton here to the right, and that's 50 Newtons. And then we're going to go 30 upwards, and that's 30 Newtons. And then we're going to have negative 10 to the left, and that's negative 10 Newtons. And you say to yourself, okay, well, how do I calculate our resultant? You always draw your resultant from tail to tip, from the first tail to the last tip. And this should be familiar for us from when we worked on displacement. So we kind of draw this diagram out, and we have our resultant there, and I put it in blue, and I'm going to label it as R. And we say, okay, well, how do I find the length of this? Well, I'm going to make a little right triangle here. And the right triangle is going to have a base of 40 Newtons, because we had 50 and negative 10. I'm going to write out actually that force equation for that x-axis. Our Fx is going to be, and this is the F net on the x-axis. If remember, net force, this is the net force on the x-axis, is going to be 50 Newtons plus negative 10 Newtons. So our Fx was that 40 Newtons, positive 40 Newtons. How about the Fy? Well, the only force acting in the y direction was that 30 Newton force. So our Fy is simply 30 Newtons. You do want to keep in mind that those x and y components are separate. It's going to matter a great deal very soon. But for now, just notice we have their net force on the x-axis. Remember, this symbol here means summation of forces. You can think of this as being the same as the F net on the x-axis. And this would be the F net on the y-axis. And how do we combine these? Well, it's a right triangle, so we can use the Pythagorean theorem. A squared plus b squared equals c squared here. And you would get a 50 Newton resultant force. You could find the direction of this by using inverse sine, for example. And you'd actually get the angle, 37 degrees north of west. So if I'd say, okay, well, what is the resultant force on this object? Well, I would take all this work, and I'd say, okay, well, I found it. It's 50 Newtons. If they asked for just the magnitude, it would just be 50 Newtons. And how did I get that magnitude of 50 Newtons? Well, I have 40 this way, because we have 50 over, 10 back. And then we have 30 vertically here. So I want to note Fx and Fy, you calculate them separately. How do you combine them? You can use the Pythagorean theorem. So to go from your components to your resultant, you use the Pythagorean theorem. Now, let's say I wanted to find the acceleration on this object. Well, I'd say, okay, well, how do I find acceleration on an object like this? Well, net force, and now notice here, I'm not using either axis, not x or y. This is the total net force is equal to mass times acceleration. And that's Newton's second law, right? You want to remember that's Newton's second law. So let's use that to find our acceleration here. It's a 10 kilogram object. So we're going to have a 50 Newton net force because I combine the x and the y using the Pythagorean theorem. And it's equal to a 10 kilogram mass. That was given in the beginning of the problem, times our acceleration. You divide, and you get the acceleration on this object, which is 5 meters per second squared. So we have a 5 meter per second squared acceleration. Now imagine I said we're going to add one more force, and the force that I add to this will bring the object into a state of equilibrium. And that's a new phrase for us, equilibrium. And what equilibrium means that F net is equal to 0 newtons. It means there is no unbalanced force acting on the object. If the F net is 0, there's no unbalanced force. Well, then what force has to be added to produce equilibrium? The opposite of whatever the F net is. This would produce equilibrium, and we'd call this the equilibriant force. And it counteracts the net force here. So we'd have this net force here, 50 degrees northeast. This equilibriant force would also have a magnitude of 50 newtons, and it would be sort of backwards and to the left there. It would be in a southwest direction, or a southeast direction. If this was northwest, this would be southeast. So here's kind of the opposite. The equilibriant is simply the opposite of whatever's already there. If your original force was a 4 Newton force to the right, then produce equilibrium, we would need a 4 Newton force to the left. And those would cancel out, and that would give you an F net of 0 newtons. If something is in a state of equilibrium, there's a couple of things we know about it. If it's in a state of equilibrium, F net is 0 newtons. If F net is 0 newtons, according to Newton's second law, some more things you know. Acceleration is 0 meters per second squared. The object will not speed up or slow down without an outside force. If all forces are balanced, you do not have any outside unbalanced forces. So acceleration is 0. You can make a chart of this, and you'd have acceleration right on that x-axis. That'd be acceleration time graph for this object. Velocity is constant. It could be 0, but it's definitely constant because of Newton's first law. Because of Newton's first law, an object in motion stays in motion at a constant rate unless acted on by an outside source. So if we had a velocity time graph for this object, it would stay at a constant velocity. This is if all forces are balanced, if the object is in a state of what we call equilibrium. And so what would happen on our displacement time graph? Well, our displacement time graph would simply be linear for this object because it has a constant velocity once again. So, things to note here. Resultants can be combined using the Pythagorean theorem. Resultants can be combined using the Pythagorean theorem. Your equilibrium can be found by just drawing the exact opposite of whichever vector you find using the Pythagorean theorem, or drawing a tail to tip. You could also draw these tails to tip. Like if I had this and this, my resultant would be right here. You can, of course, always draw these tail to tip as well. The equilibrium counterbalances whatever your net force is. A non-zero net force produces acceleration, but if an object is in a state of equilibrium, net force is 0, there are no unbalanced forces, velocity is constant, and acceleration is 0 meters per second squared. And this all matches with Newton's laws.